My guest today is Professor Peter Gorham, who is Professor of Physics at the University of Hawaii at Manoa. His research interests include neutrinos and cosmic rays. Welcome, Peter.
Welcome. Yes, good to see you, Gill.
Yeah, thanks for doing this. So you sent me a number of papers. Some of them are a little technical, and I have no background in astrophysics or particle physics, and so I'm hoping to learn something from this conversation. So the first one is observation of the Askaryan effect, coherent microwave Cherenkov emission from charge asymmetry in high energy particle cascades. So you say here we present the first direct experimental evidence for the charge excess in high energy particle showers predicted nearly 40 years ago by Askaryan. So, so we need to get a few definitions first to sort of try to understand this. So Askaryan effect, should we start there or should let's start defining neutrinos. So I was wondering, are neutrinos part of the standard model that we currently have, or are they outside of it?
Yeah, absolutely. The neutrinos are among the few fundamental particles that we have in the standard model. So they are in the lepton family. So they share the same kind of family characteristics as the electron, its antiparticle, the positron. And in addition to the electron, in the charged leptons, we have another unstable particle called the muon, and of course an anti-muon. And then there's a third generation in that family of charged leptons that's called the tau particle, or the tauon, and its antiparticle as well. So those three generations are the standard model lepton family, and leptons are considered to be particles that are not composite. So protons and neutrons, which make up the nuclei that we're familiar with, physicists consider those to be composite particles. They're made up of another type of particle called a quark. And there's a lot of complexity in that part of the standard model, which I will kind of steer clear of today. But the lepton family is particularly simple, and interestingly to us physicists, neutrinos also come in three generations, and they seem to mirror the charged leptons, which we know about. So the electron is a point-like charged particle fundamental to electricity. It's some of the theories in physics that are associated with it are among the most beautiful theories. The quantum electrodynamics associates electrons and photons and all of the dynamics associated with their interactions. And that's, in some have called that the crown jewel of theoretical physics. Muons and tauons, because they're unstable particles, they're not as well known to the public as the electron is. We don't learn about them as readily in our early education, but they also play this very important role in the standard model because they complete the lepton family. Neutrinos, to the best of our knowledge, are the other stable part of the lepton family. But they are very different than their charged particle cousins. They're, as far as we know, completely uncharged. And so they're, in effect, they're neutral particles, and they also have very, very low interaction cross sections with all of the other matter in the universe. When I try to explain this to my students, what I'll tell them is that if you think about it in terms of the size of the particle as being a characteristic that represents its interaction probability, then a neutrino, a typical garden variety neutrino, is as much smaller than a proton as a proton is smaller than the entire Earth.
Oh, wow.
So the scale of neutrino interaction probability or size, if you will,
Mm.
is such that it's so many orders of magnitude smaller than the nucleus of
Wow.
the
Okay.
of the of the atom,
Yeah.
that it almost seems to exist in its own separate universe.
Well,
It
I didn't. So I
barely
didn't get.
makes
Yeah.
contact with our universe, if you
Yeah.
will.
Yeah. Yeah.
Um,
I didn't quite appreciate the size of it. So my understanding is that we thought they're also massless for a while.
yes, that's right.
And then now I think the current understanding is that they have a very minute mass.
Yes, and this is a great puzzle in physics, and it
Yeah.
remains a puzzle. Our standard model of physics, it has a lot of explanatory power. It unifies a bunch of different forces in ways that are very satisfying in physics. But neutrinos just don't obey any of the symmetries that we like.
Yeah.
So, photons, to the best of our knowledge, the partner to the electron, the propagator for the electromagnetic force, they are completely massless.
Yeah.
Neutrinos are, although they're not a propagator per se, there's nothing that prescribes that they need to have any mass at all.
Mm.
And there's nothing that prescribes that they shouldn't have mass. We just don't have any theory about what that mass should be.
Mm.
And so we don't have any explanation for the masses that are observed. But the
Yeah.
consequence of the neutrino being massless is that it changes the way that neutrinos manifest their existence with other particles. They now, because of that mass, their states are a mixture of what we call their sort of physical states. So we have the three
Yeah.
generations, each of which is assigned to its lepton partner, the electron neutrino, the muon neutrino, and the tau neutrino. Those are the sort of
Three varieties. Yeah.
physical states.
Yeah.
But those are not the states that the masses occupy.
Mm.
And it's what physicists call this is these are it's sort of mixed up, if you will.
Yeah.
The
Yeah.
mass, we call them eigenstates. Those are sort of the natural states, the mathematical location that they should be. They are not the same as the physical eigenstates. So
Mm.
because of that, neutrinos are shapeshifters. An
Mm.
electron neutrino mixes with a tau neutrino, and sometimes when you try to observe an electron neutrino, it has shapeshifted into a tau neutrino and will disappear.
Yeah.
So
Sounds like Harry Potter.
yeah, exactly. I mean, and we have no theory for this other than
Yes.
we can describe the mixing very accurately because we have good mathematics for that, but we have no fundamental theory as to why that should be the way it is.
So are we hypothesizing in some ways that there's a mass, but we don't really know?
No, in this case, the mass is very well established, and it's
Okay.
necessary for the phenomena that we observe in the neutrino sector. The mass is a proven consequence
Mm.
of that, and it has other consequences as well in terms of cosmology, which are
Yeah.
something that I don't really need to go into. But from the
Yeah. I
point of
want
view
to.
of
Yeah.
yeah,
So sorry to interrupt. So I want to just very, very quickly go into it. So we have this dark matter puzzle. Um, so will neutrinos be a candidate to fill that gap or not really?
unfortunately not.
Okay.
That was a very early hope that perhaps neutrino masses could play a role in dark matter, and we've almost completely eliminated that possibility.
Okay.
We've definitely eliminated the possibility that the neutrinos we know of are part of the dark matter. Their masses are just too small and their number density isn't high enough.
Okay.
However, the story of neutrinos is not a done deal yet. There can be what are called hidden sector neutrinos.
Mm.
These are also called sterile neutrinos because not only are they sort of very, very difficult to detect, they don't interact with normal matter at all.
Mm.
And so the only time you would ever be able to detect a sterile neutrino is through some secondary process where other sort of fundamental physics laws get violated. This is not a standard model solution. Okay, so the standard model neutrinos cannot be dark matter, but we haven't yet excluded that there could be a kind of non-standard sector of neutrinos that could be very massive. In fact, they could have masses that are even higher than quarks and protons.
So they sort of fit into the WIMP hypothesis in some ways.
We can't exclude them yet, and that's been a very active part of research to try to set limits on these so-called sterile neutrinos.
So even sorry to interrupt, Peter. So even if the sterile neutrino hit the nucleus of an atom, we still can't see it. We still can't find the effect.
A neutrino can hit a nucleus, and it can hit an electron as well. It's just that it happens extremely rarely. And so in order for you to see that happen, the number of neutrinos that pass through that nucleus has to be enormous. This is kind of harks back to this issue of the neutrinos seem to be in a completely different universe, if you will, but they very occasionally slip up and hit something in our universe, if you will. I mean, this is obviously a little bit of a whimsy that I'm pursuing here, but it, from a practical point of view, it's almost as if that were the case. We can prove their existence, but only because there are so many of them that occasionally 1 in 10 to the 18th of these neutrinos will sort of miscue and hit a nucleus, and then then the fireworks can be produced, and we can see that.
Yeah, so it's a nightmare for experimentalists.
It is
going into this field.
Yeah, there are some of us in physics who love these kind of challenges, and it is a little bit of kind of self-torture, if you will, because I spent a good portion of my career just measuring zero. And that gets pretty old after a while. So,
so let's talk about the Ascarian effect. And so in this context, what exactly is Ascarian effect?
Okay, so the historical context here is that there was a Russian-born Armenian physicist, Georgian Ascarian, in the 60s. And he was actually quite brilliant. He invented a few ideas, one of which I think I may be misremembering this, but I think he invented the idea of laser ablation, and it could be that or something else that he did actually led to a Nobel Prize for another physicist who invented it later, an American, in fact, and that gave Ascarian a real sort of heads up. What's going on? How did I miss that? He tended to just throw ideas out there at the institute he was at and didn't publish them. And so this particular case where an idea that he had, which people remember, and he didn't publish it, ended up giving somebody a Nobel Prize. So then he got very nervous and he started publishing everything. And he had an idea that at that time, the world was now waking up to nuclear energy, nuclear power. The cyclotron invented by Ernest Lawrence had revolutionized particle physics. And we were now able to create particles that were as high in energy as the cosmic rays, which people had known about for a long time. These are particles that come in from outer space with very high energies, and they crash into matter in the upper atmosphere, and they produce showers of secondary particles because their energy is high enough that they can create new mass from their energy.
They're not neutrinos. The cosmic rays are something else, typically.
They can be anything. They can be any cosmic particle. Yes. Neutrinos are potentially a cosmic ray particle, although much more rare than any other kind of the average cosmic ray particle. The typical one is just a nucleus. either a
Yeah,
hydrogen or
like a
helium
hydrogen
nucleus.
nucleus. Yeah, okay. Yeah.
Yes, yeah.
Like,
So a proton, and that
yeah.
proton has a high interaction cross section for hitting air. And after a few kilometers of even the upper atmosphere, it will likely interact with another nucleus of nitrogen or oxygen, and that will create then a splash of secondary particles, because from Einstein's equation, energy equals mass times the speed of light squared. So if you have enough energy, you can create new mass.
Yeah.
And those cosmic rays have that kind of energy. They have energies that are far in excess of the mass energy that they themselves have. And that secondary mass energy that they have can create a whole host of secondary relativistic particles. And we call that a cascade.
Yeah.
Um,
I don't know if I'm thinking about this correctly, Peter. So E equal to mc squared still stands, right?
yes.
So really there's only two parameters, which is mass and velocity, that ultimately determines it, right?
Um, the it's actually the actual equation that Einstein wrote down was energy equals there's another parameter, gamma, times
Oh,
the mass times the speed of light squared. So
okay.
if for a particle at rest, its
Yeah.
mass energy is just equal to its mass times the speed of light squared. But for a
Oh,
particle that's moving,
okay.
there's another factor, we call it gamma, the Lorentz gamma factor, and
Hmm.
that includes a velocity term. So you're correct. The mass matters, but the velocity only matters if the particle is moving relative to the reference frame that you're in.
Oh, wow.
So
Okay. So
remember,
I
relativity still applies here. So if your particle is at rest,
right.
Einstein said, then its total energy is just its mass energy. There's no kinetic energy. But if the
Oh, wow.
particle is moving relative to our frame of reference on the
Right.
Earth, that particle now has both kinetic and mass energy. And the
Yeah, I
kinetic
didn't quite.
energy is represented by the velocity.
So I didn't quite appreciate. So this sort of, I was thinking, I mean, neutrinos show very, very high energy levels. And I was thinking these things have very low mass. And so why do they get this very high energy levels?
Right.
And the
Yes,
answer is they're moving close to the speed of light.
that's correct.
And E equal to mc squared is applicable when the particle is sort of at rest, so to speak.
Without the Lorentz gamma factor, the particle at rest has the energy equal of its mass times the speed of light squared. So the mass energy of a neutrino at rest is very, very low.
Very low. Yeah.
A few electron volts, just enough to um, to move an electron, very slightly. Okay,
Mm.
it's very, very low amount of energy if you blew up a neutrino somehow. But
Yeah.
neutrinos, because they have such low mass, they're quite easy to accelerate if you can manage to find some way to hit them
Yeah.
and knock them into a higher velocity.
Like a black hole or something, say a little bit about the cosmic ray concept. So these are stuff coming to us from outer space,
That's right.
and it could be created by a lot of different phenomena, black holes being one
Yes.
of them, and quasars and others. So talk a little bit about, what exactly are cosmic rays? How did we find them? And how do we sort of look into it in more
So
detail?
they were actually discovered almost a little over 100 years ago by uh, a scientist named Victor Hess. He was flying in a balloon, in fact,
Yeah.
and he noticed that at that time people had already discovered radiation and realized that photographic films were developed in the presence of radioactive materials. So Victor Hess flew some of these films with him in the balloon, and noticed that the higher he went, the more exposure he got on his film.
Mm.
And over a series of experiments, he was able to establish that there is a form of radiation coming in from outer space that is similar to radioactivity.
Yeah.
And at the time, no one really knew what that was. They knew radioactivity had something to do with with unstable elements. But it took the next few decades for people to understand what was happening to produce this high levels of radiation as you went higher and higher in the balloon. What we know now is that cosmic rays are subatomic particles of all kinds.
Yeah.
Even heavy nuclei. You can have iron nuclei, and they are generally completely stripped of their electrons, so fully ionized material.
And they're moving close to the speed of light, or
much of it is moving very close to the speed of light. A lot of cosmic rays come from the sun, in fact. Just the solar wind. You can think of the solar wind as being a form of cosmic rays. Most of that is protons at relatively low energies, but still high enough that moving a significant part of the speed of light. But we also observe cosmic rays moving at enormously high energies, far more than anything we can do on Earth with our best particle accelerator, with the Large Hadron Collider in Europe. The Large Hadron Collider can produce energies of around 10 tera electron volts, so around 10 to the 13 electron volts. You can think of that electron volt unit as just like it feels, it's voltage, all right? So 1,000,000 volts can make an energy of 1,000,000 electron volts for a single electron, a single charged particle. In lightning, for example, we see 1,000,000 electron volt energies, and they do accelerate electrons and even make gamma rays sometimes. But cosmic rays have energies up to a zeta electron volt. That's 10 to the 21 volts.
Okay. So nine orders of magnitude higher.
9 orders of magnitude higher than the Large Hadron Collider. And we've been seeing these since, I think, the 30s, 40s, and 50s. People have been measuring them. They've measured the particle spectrum, the number of particles as a function of energy. And it is a very steeply falling function, but we still see these enormously high energies in particles. And we don't yet have a complete theory on what could produce those. Of course, the smoking guns that we suspect are things like black holes and active galactic nuclei, and the very strong magnetic fields that surround them. When you have a charged particle, magnetic fields are very efficient at accelerating charged particles if you wait long enough. The charged particle will bounce back and forth in the magnetic field, and gradually it will gain energy. So if you wait millions of years, perhaps you can achieve these very high energies. But that's
not the case for neutrinos.
Well, so neutrinos themselves cannot be accelerated that way. However, what happens back to this particle cascade problem? When that proton collides with that nucleus and makes that splash of secondary particles, many of those secondary particles are unstable radioactive kind of particles. So for example, pi mesons, muons, tauons, other kinds of unstable radioactive particles. And many of those unstable particles decay with neutrinos as one of the secondary byproducts.
I see.
In fact, that's a very characteristic thing for neutrinos, which participate in what is called the weak interaction. Their primary contact with our universe comes through radioactive decay. Radioactive decay almost always makes neutrinos. And that was how they were first discovered, was through the missing momentum that was observed in radioactive decays. Enrico Fermi and other scientists realized that if you look at a radioactive decay and you measure it's like a billiard ball breaking or a billiard break, you see all the balls going, and you can add up all the momentum from those balls. And if it's not all accounted for, where did the rest of it go? Momentum has to be conserved. So that was how Fermi discovered the neutrino.
So let me see if I understand this. So neutrinos is sort of a product of some collision, such as protons and cosmic rays with atmosphere or something like that. So it's never the case that we have neutrinos showering from very large distances at the velocity of light. I mean, they're produced in a secondary
Yes,
process, right?
that is correct. But the secondary process itself may happen in the atmosphere of a black hole, for example, in the accretion disk near a black
Oh,
hole,
okay.
or
And they
in the
can still
magnetic
reach
field.
us from there.
Yes. So it
Okay.
could happen, and it's very likely to happen in those regions where this very, very intense radiation field and
Yeah.
accretion field exists. So you have particles that are being accelerated, but they're colliding with material in the vicinity of the black hole. They're colliding with the very intense photon field that's present. And
Hmm.
those collisions then, which create these secondary cascades in the atmospheres and of neutron stars or black holes, those can make neutrinos. So that's a typical scenario by which you can make very high energy neutrinos as the secondary daughter particles associated with some primary cosmic ray.
This is a cascade. So there's some directional implications here. So if we find something on Earth, um, so we have this blazers and we have other stuff
Mhm.
going on. So we can actually look back and sort of figure out where they came from, or
In the case of neutrinos, yes, that is
yeah.
one of the attractions, one of the reasons why astronomers are interested in neutrinos is that they share with photons that one characteristic that only those two particles really can, and
Hmm.
that is they are uncharged. So once you make a neutrino and it travels across the universe, it will not be deflected
Yeah.
from its original source except by gravity.
Right.
And that makes it very attractive for astronomy,
Hmm.
because if we once we can develop our tools to observe neutrinos efficiently, which is the big difficulty we have now, then we will be able to see the universe in a completely new light.
Hmm.
And that process has started, very, very, we're taking baby steps along that trail, but we still have a long way to go. And most of my career has been trying to advance those baby steps. And I still feel like I'm a toddler at this point.
So we could have neutrino lensing, so to speak.
Yes, yes. It will be um, very similar to what happens with
Photons.
gravitational lensing of photons. So
Okay.
if we were able to detect neutrinos with the incredible efficiency by which we can detect photons, then we could observe neutrino gravitational lenses. That is correct. But we're a long way from that now, just because they don't cooperate with us very well in that regard.
Yeah, it's a ghost particle, so to speak. So,
Mm.
so I want to go into Anita. I mean, this is something that you spend a lot of time on, and a fascinating experiment. The Antarctic Impulsive Transient Antenna, ANITA, ultra high energy neutrino detector, design performance and sensitivity for 2006 and 2007 balloon flight. So this is when it first happened, ANITA 1, I would imagine, right? So
Yes.
you say here, after the confirmation of Ascarian effect, you and a group of scientists with cosmic ray, neutrino, and scientific ballooning expertise proposed that a NASA long duration balloon payload launched about Antarctica in the austral summer polar vortex could achieve, we're going through a polar vortex right now here, could achieve a
Yeah.
sensitivity to cosmic ultra high energy neutrinos that would exceed that of any other detector. So 2006, Anita won. So what's the traction of the ice in
Yep.
uh,
That's a good question. Why
yeah,
why go south? Why go down and
yeah.
get frozen down there? So I didn't complete the story with the Ascarian effect. So let me give you
Yeah, yeah.
a very
Sorry. Yeah,
quick
yeah,
overview there, because we
yeah,
kind of need that.
yeah.
So Ascarian hypothesized that these cascades can produce radio impulses, and he actually proposed that it would be an excellent way to look for high energy cosmic particles like
Oh,
neutrinos, because you could choose some very large natural media,
yeah.
and then look for a radio pulse originating from from Antarctic ice, for example. So Askaryan's hypothesis had not been confirmed as of after he had proposed it. It was interesting. Russians took it for granted that this had to be right.
Yeah.
And they were right, of course. Russian physicists, often don't think something needs confirmation because to them it's theoretically obvious. And
Right.
us Americans were not as smart, so we thought, well, we better first confirm this before we spend a bunch of money on it.
And we need
Um,
experimental evidence before
yeah,
we
so
accept anything. Yeah.
we did an experiment. It was a roaring success. We were at the Stanford Linear Accelerator, and the very as soon as the particle beam turned on, we were using oscilloscopes to kind of make the measurements of these microwave pulses that we expected to see, and all of our oscilloscopes just lit up blindingly, blinding flash of light, and we knew that we had it. So that was very successful, and then at that point we had a tool. And we said, well, what can we do with this effect? We know that particle cascades now make a pretty strong radio pulse. It's nanosecond, sub-nanosecond pulse. It's not really like anything else in high energy physics. Can we use it to identify something, some process? And one of the first things that we did was have a workshop with some of our colleagues and other people that were interested in this. And we started looking at ideas, and we tried all kinds of crazy stuff, maybe 30 different brainstorming ideas. How could we do this? But the one that stuck out like a sore thumb above all the others was flying a balloon payload over Antarctica. And so we decided to propose that to NASA. We would look for cosmic neutrinos because it turns out that Antarctic ice is the clearest natural medium on Earth for both for optical light and for radio waves.
Oh, wow.
In the optical, we don't think of it as being clear because of the scattering of the snow and things like that. But if you were able to get down deep into the ice, the clarity is actually utterly remarkable down there. But
you have
even
less
more,
noise? Less noise also?
Yeah, less noise. Once you get down below the surface, there would be less noise. So there are experiments at the South Pole that are trying to do this with optical, measure the optical flashes from neutrinos, and that has been one of the successes so far. For what we wanted to do, we wanted to really go for these very highest energy neutrinos, the ones that are off scale, the ones that are super extreme, and for that you don't get enough volume of material if you try to do it with optical light. They produce both an optical flash and a radio flash. And in the optical, the attenuation length, if you will, the distance over which things kind of fade away is around 100 meters or so. And that doesn't seem like a huge distance, but if you lay some panes of glass down, if you had a block of glass in front of you, it would start to look darker after maybe a meter, even the clearest glass on Earth. So ice is 100 times more clear than the clearest glass on Earth. But in the radio, it's even more striking. In the radio, you could go for 1 or 2 more kilometers before that radio signal would start to fade out. And so it is, in that sense, the clearest natural medium for electromagnetic waves on Earth, for a solid, that is. Obviously, the atmosphere is very clear as well, but it's 1,000 times less dense.
Yes, so, it's counterintuitive. So I would imagine this ice is really pure ice, right? That's attraction.
That's Antarctica. We have people don't realize that the ice there is more pure than the purest drinking water on Earth. In any municipal area.
Yeah.
There are, there is entrained dust and other stuff in the ice, but it's at such a minuscule level compared to any other kind of water source on Earth that Antarctica is utterly unique. And it's kind of, for those of us who have worked in Antarctica, it is gut-wrenching to see what's happening on Earth and the danger that we're facing for the entire cryosphere right now. But that's kind of a topic for another day, I guess.
You better finish the experiment soon.
Yes,
because we may not have it.
Yeah. We may not have as long as we think. Certainly in Greenland, that could be true. So, ice is incredibly clear. If you had radio eyes and you flew over Antarctica, you would see right through the continent, and you could see the mountains below it, 2 or 3 kilometers below the surface. Sometimes 4, sometimes even 5 kilometers deep, that ice. Because that's so deep and there's so much mass there, neutrinos are at risk of colliding with something. And even though they might collide 3 kilometers deep, we still could see that radio pulse because it'll propagate up through the ice and be refracted out to a balloon that is flying in a stratospheric orbit over the continent. So
so Anita 1, you say here, has yet to detect any cosmic neutrinos, but has placed stringent limits on their fluxes. Right. And we want to talk about Ice Cube too. So we're talking about a balloon here, right, in Anita 1?
Yes.
Fundamentally? Okay. And so you go on to sort of other experiments. So you say here, observation of ultra-high energy cosmic rays with Anita balloon-borne radio interferometer. In the search for ultra-high energy neutrinos, which are very penetrating fundamental particles, we talked about that Anita's sensitivity was such that ultra-high energy cosmic rays were observed via their radio signature due to interactions in the Earth's atmosphere. Yes. This is a pretty important thing because we have neutrinos coming from the sun too, right? So you have to somehow differentiate between these guys traveling a long time than something that traveled 8 minutes. And so how do you really differentiate this?
Well, so the neutrinos that come from the sun are at far, far lower energies than the ones that we're going after. Okay. That's really the difference. Neutrinos from the sun kind of peak in let's say the 1,000,000 volt energy range. The neutrinos that we were interested are 1 billion times 1 billion volts.
Okay, so above. Big difference.
Very, very big difference. Yeah. Okay. If a solar neutrino hits a nucleus in the ice, all it will do is actually create a nuclear excitation with very, very little secondary radiation. Okay. If a neutrino at 1 billion electron volts that comes from, say, an active galactic nucleus, a black hole from across the galaxy or from across the universe, if that one collides with a nucleus in the ice, it doesn't just excite the nucleus, it blows it to pieces and then creates a whole bunch of secondary energy almost in the form of a lightning bolt in the ice. And that lightning bolt travels for 10 or 20 meters through the ice, making a really monstrous burst of radio waves that we can hear, even if it's 600 or 700 kilometers away, we're going to hear that burst.
Yeah.
And so that was the reason we were able to get NASA support, even though no one had ever seen any of these, and still we haven't seen them directly from neutrinos in 2 decades of searching. Even we were able to get support because the physics of that process is inescapable, and it's been verified in every other way. So in that sense, we were searching for something which, if neutrinos are there and we keep listening, eventually we will hear them. And IceCube has fortunately achieved that at significantly lower energies. So we still haven't gotten to those billion volt cosmic ray originated neutrinos, but we are seeing them at energies 1,000 times lower, and that's very encouraging. It means that the door is beginning to crack open on the universe with regard to high energy neutrinos. In the process, though, as you said, we were sensitive to other stuff that we didn't expect. And it turned out that normal high energy cosmic rays up to a billion volts plus, they were also hitting the upper atmosphere. They were making showers of particles in the atmosphere. And some of that was producing radio signatures as well. And we started to see those, but they were actually in a different channel, if you will, than the ones we were looking for. I use the word channel in the same kind of sense as when you tune your FM radio,
Yes.
You get to a different channel. Well, that wasn't the one you were looking for.
Rock versus pop, so to speak.
That's the country music channel. No, that wasn't the one I wanted, but okay, it turns out there was country music playing, and we were listening to the neutrino channel and hadn't heard anything at all. So we thought, well, let's go and look at this country music channel over here. That was the cosmic ray channel. And, I say it rather glibly, but it actually was in a very distinct kind of physical mechanism that we were looking at. They were radio bursts, but they had very different characteristics. Still, our sensitivity was such that we recorded both of them. And that had not been achieved before for cosmic rays. And so, that was interesting. It wasn't our main event. So we published that paper. It was of interest to cosmic ray physicists, and certainly some of us were very interested in that process as well. And we went on from that to go back to look for neutrinos. We thought, well, okay, now we can be listening to this other channel to help set our sensitivity and confirm it. But ultimately we want to try to find neutrinos, because that's the really exciting part of this. But so that wasn't the end of the story.
Sorry, Peter. So if I understand this correctly, so the theory is well established. So you could actually predict things. So you knew what you were looking for.
Yes.
And if you found it, then it sort of proves the hypothesis on the table, right?
If we had seen neutrino signals, all the evidence was that they would be utterly unique with virtually no background. The only possible background in Antarctica is from anthropogenic sources, that is man-made radio pulses. And those, unfortunately, human activity can mimic the kind of
it's those signals. Guys in New Zealand. We have to get rid of them.
It's what it is the guys driving around with the ski-doos, and a spark plug gets loose, and then of course it makes a radio burst, and even the piezoelectric lighters. If you flick a piezoelectric lighter in Antarctica anywhere, and we're on the horizon 600 miles away, we're going to see that. So that's how sensitive Anita was. And so we did have to eliminate all of the anthropogenic noise. There are camps in Antarctica. People are doing activities that can create radio noise. Overall, it's much, much quieter there than anywhere else on Earth, but still we had to eliminate those possibilities. So we could never allow an event to be a candidate if there was a repeat at that location. No neutrino would ever repeat. Lightning doesn't strike twice in that case. So those would be excluded. Anytime there was multiple activity at all, that would indicate something anthropogenic. That was our going in position. So we had to look for isolated events with the characteristics of a neutrino signal. And to date, we have not seen any. Well, for each flight, we've had 1 to 2 candidate events, but they could be explained as potentially just the leakage of background. However, that's not the case for cosmic rays.
Right.
For every flight, we observed a series of cosmic rays.
Yeah. In the balloon, right?
Yes. Yeah. From the balloon.
Yeah.
And they have characteristics that were interesting to us because they in some ways mimic neutrinos, but as I said, in a different channel. But they also allow us to kind of establish the sensitivity of the process, and that's always a good thing. However, in some of our earliest data, we had one cosmic ray that was identified by the analyst who was doing that, and that that particular cosmic ray was excluded by the analyst because it didn't quite fit what
It makes
we
sense.
thought it
Yeah.
should be.
Yeah.
And so we didn't think much about it until a year or two later. We were at a conference. I remember talking to one of my colleagues, and he suggested that even if we could see one particular type of event, that might be the signal of a different channel for neutrinos, in which neutrinos act like cosmic rays in some specific way, but in other ways they're very different. And so we went back and looked at that data, and sure enough, that one event had those characteristics. And specifically, it had the characteristics of a cosmic ray as if it had emerged from the ice, not coming down from the atmosphere above.
So this is what you call the upward pointing cosmic ray-like events.
That's correct. Yes.
Okay.
And the reason we knew that it was upward and not downward. So the downward pointing cosmic rays, we actually see them when they reflect off the ice sheets. The ice sheets actually are good smooth surfaces in the radio wavelengths, and they make a good reflector. So when we look down at the ice, we're looking for neutrinos emerging from the ice, but we also see the cosmic rays kind of reflected from above, and that we'll see dozens of those in that process. And every time something reflects in an electromagnetic wave, there is an inversion of the polarity of that wave. That wave, we see this even in water waves. If they hit a wall, they kind of flip over. And so we saw in every case, we saw those kind of flipped inversions of the polarity of the wave. That was a normal thing. We also saw a small number of cosmic rays that came straight at us through the atmosphere without without reflecting off the ice. And those were not, these are the Earth
what you call the skimming.
That's right.
Cosmic rays.
Skimming cosmic rays, a very interesting type of cosmic ray event which never intersects Earth. It just takes place in the upper atmosphere. Particle comes in tangential to the Earth's surface, interacts in the atmosphere, makes a cascade, and the cascade just dissipates without ever having hit the Earth. So it creates a certain amount of radiation at high altitudes. And we saw those as well, and they were not inverted. They had all the other characteristics of cosmic rays, but without that reflection effect of inverting the wave.
So I remember, Peter, reading, I think this is where the UK science journalists went a little bit nuts when you saw the upward going cosmic ray.
Yes.
And they thought it was from a different universe or something like that, right?
There was, there was some tabloid journalism that took place. And it was not something that we initiated. We were just reporting what we had observed. But people like to speculate, and in this case, I think speculation in science is actually quite valuable. But there is a point at which it crosses the line, and there was no evidence for anything as bizarre and extreme as the journalists had proposed. But it did create this kind of tempest in a teapot for a while. The actual observations, though, are still unexplained. The parallel universe idea, there's no evidence for that, and so I don't think there's much more to be said about it.
Yes.
But what we observed physically was a cosmic ray that didn't have that polarity inversion. And we could not find, and so, okay, one event is not enough to ever prove anything. You have to confirm it. You have to see it again. So we kind of wrote the paper and left it as it was. There wasn't much else to be done with it. And then we went and we flew another flight. We flew a third flight. And in the second flight, we had actually, without realizing it, we had already built the instrument when we discovered this anomalous event.
Mm.
And we had turned off that channel because we thought, well, this channel is not so interesting. So we didn't have that
Right.
channel for the second flight, and we couldn't actually see if there were any more of these
There could
events.
have been some, but you didn't pick it up.
We
Yeah.
just didn't have that part
Yeah.
turned on. And so, of course, we learned our lesson and licked our wounds. And on the third flight, we went back
Yeah.
and we reactivated that channel and made sure that it was fully sensitive. Um, and and we were very careful to do what is called a blind analysis of the data after
Yeah.
we got it, so that we didn't want to bias the possibility that we would see one of these events because we really wanted to see one. We
Mm.
kept ourselves completely blind to the polarity of the event. That's what tells us whether it was inverted or not inverted,
Yeah.
and didn't open that box until the very, very end when all the analysis was complete. And when we did that, we had about another 30 or so of these
Oh, wow. Okay.
events, but only, and all of them looked like the normal polarity we would expect, except for one. There
Mm.
was another anomalous event. And so because we had done a blind analysis and we've been very, very careful, now
Yeah.
we were starting to take notice of this. This is another event. It was actually much cleaner than the previous one.
Mm.
Very, very much a garden variety cosmic ray event.
Mm.
There was nothing about the event other than that polarity, which indicated it was anything other than a cosmic ray. And
Mm.
so we had to conclude that there was either some physical mechanism which could occasionally flip the polarity of the electromagnetic wave,
Mm.
or we were observing something that was emerging from the ice and
Yeah.
cascading in the atmosphere in an upward direction rather than cascading in a downward direction and then reflecting the radio wave off the ice where we would observe it.
Mm.
Um,
It seems to me, Peter, that this is a problem that is potentially very amenable to machine learning, right?
Yeah, I think
Yeah.
you're absolutely right, and we have actually used machine learning
Yeah.
methods in trying to recognize these events. So that is something that we've adapted to our analysis code. For in our case, it actually is quite effective,
Yeah.
but our biggest problem is still the anthropogenic background. We
Yeah.
cannot
Yeah.
exclude the human element completely. And
Yeah.
so for each of these events, we did a very careful analysis of the probability that this could be a background event. And in each case, the probabilities were in jargon terms around 3 or 3.5 sigma.
Yeah.
That corresponds to about a 1 chance in 1,000 that these were
Mm.
background events.
Do
So
the
that's not
penguins
an
do
what's
the
that?
penguins interfere?
As far as we know, penguins don't have piezoelectric lighters, but if they did, that would be a problem for us.
They might be
So
walking around with an
that's
iPhone. I mean, you never
they
know.
might,
Yeah.
they might, yes. They may have planned it all out at this point. They are very cute, and they might have thought that was another way to be even
So
more
so
cute. So
so you ran so there are 4 missions. So Anita 4 um, performed another very careful search for similar anomalous events, found 6 cosmic ray-like events in geometries that were tangential to the Earth. So why is it that things coming tangential? I guess it's in combination with the polarization that we find it interesting, right? I mean, things could be coming tangential pretty easily, I would imagine, right?
well, there's a kind of a full hemisphere of directions that cosmic rays can come from.
Yeah.
If we don't count the ones that come from below the horizon, we don't know what those are. But when we're up at orbit, on orbit in Anita, the horizon is depressed below us by about 6 degrees.
Hmm.
So it's below the horizontal by about 6 degrees. The atmosphere, as observed from the balloon is above the atmosphere. As observed from the balloon, the atmosphere occupies a little thin band about 2 or 3 degrees wide at the horizon. So
Yeah.
very, we've seen this from space shuttle photos that our atmosphere is this very, very thin layer,
Yeah.
and that thin layer we would occasionally observe cosmic rays in that very thin layer. Those are the skimming events.
Yeah.
But there isn't very much solid angle there compared to the full hemisphere. And so most of the cosmic rays are just downgoing events that pepper through the atmosphere from all directions above the hemisphere, but a very few of them can occupy that thin band. So those are the Earth skimmers.
Yeah.
And they're physically interesting because we can't observe those any other way.
Right.
We have to be up in space to see them, but also because those were the analog for something that might be Earth skimming, but coming up from below. And in Anita 4, we didn't see any more of these kind of steeply upcoming events like we saw in the previous two, but we did see 4 more events with the wrong polarity. And they were coming from just below the horizon in this case. We saw 2 of those 6 cosmic rays from above the horizon. They were garden variety cosmic rays. And then 4 more that were actually from below the horizon, but not by much, just a degree or 2. That was enough for us to distinguish them and to see that they were misfits, if you will. And in some sense, they're not as anomalous as the ones that come from even further down, -30 or -50 degrees, like the previous events. But they are still anomalies. And in this particular case, though, they could be explained as tau neutrino events. So tau neutrinos can pass through the surface of the Earth on a kind of a tangent, on a chord, if you will. And at the end of the chord, before they emerge from the Earth, they might interact with a nucleus. And in that case, they produce a secondary tau particle. So this is something in neutrino physics we call the charged current interaction. Neutrino creates a secondary charged partner, the lepton that it corresponds to. So the tau neutrino will make a tau particle, and the tau particle has a relatively short half-life. At high energies, it will travel, 5 or 10 kilometers before it decays. So that decay then is what could produce the cosmic ray shower that we see.
So that's sort of the existing hypothesis, right? So I want to finish up with your latest project, the payload for ultra high energy observations.
Yes.
PUEO. Well, how do you pronounce this?
Pueo. It's actually it's a Hawaiian word for our native owl that's here. So it's a little bit tricky for some people to say. But yes.
So you say here the payload for ultra high energy observations, PUEO, long duration balloon experiment, is designed to have world leading sensitivity to ultra high energy neutrinos at energies above 1 EeV. EeV is like 10 to the power 18.
That's right. That's the billion electron volts. That's correct.
Yeah, it's mind-boggling. So probing this energy region is essential for understanding the extreme energy universe at all distant scales. So PUEO leverages experience from and supersedes the successful Antarctic Impulsive Transit Antenna, ANITA program, which with an improved design that dramatically improves sensitivity by more than an order of magnitude at energies below 30 EeV. And you say here PUEO will either make the first significant detection of or set the best limits on ultra high energy neutrino fluxes. So this project is not on yet, right? It is.
No, it is. We are actually scheduled to fly next year. This year. It's this year now.
2025. Yes.
That's right. So we are going to fly in about 11 months, if all goes well. Okay. It took quite a while. The pandemic all of us lost 3 or 4 years in the pandemic. PUEO was already being developed prior to that, but we all sort of had to kind of suffer through that, and the program kind of went on hold, as everyone knows. But so ANITA 4 flew in 2016, and it's taken us now almost 10 years to kind of get
put
back
this
to the
new
next
one.
generation.
So will you have like just like Anita, 4 generations? Will you have 4 different generations on this as well or more?
I don't think there's any telling at this point. It's
Yes. Yeah.
I will probably I'm actually turned over the I was the principal investigator for all of the Anita payloads.
Yeah.
Um, but it was, I think, time for some younger generation people who had actually done a lot of the work on Anita to take over. So Professor Abigail Vierig at the University of Chicago is the current PI for Pueo. I'm one of the one of the co-investigators for that. And Abby and I, are have been close colleagues for many years. So it was a natural opportunity for her as a really well respected up and coming new physicist in this field to take over this problem. And she has added her own understanding and expertise in phased array interferometry to increase the sensitivity of Pueo compared to Anita. And although the payloads look kind of similar, there is one big difference, which is the fact that they are going to be able to use these phased array and beamforming methods to much improve the sensitivity. So I'm very optimistic that Pueo will crack this thing open finally, and we'll hopefully figure out what all these anomalies really are. That would be wonderful. They've been hanging out there now for too long.
Yeah, yeah. Maybe Abigail can come on the show too.
Sure, yeah, I think
You can let her
she would
know.
be great.
So in conclusion, um, you found a lot of interesting things here, both cosmic rays and neutrinos. We have Ice Cube is still functional, right? Ice Cube is
Oh,
still
yes,
going.
yes. No, Ice Cube
Yeah,
has they have really changed the landscape of the whole the high energy neutrino world because nearly a decade now, I guess, they actually made the first detection of cosmic high energy neutrinos. We still don't know exactly what the origin of those neutrinos are. They are continuing to observe these neutrinos at energies of around 10 to the 14 and 10 to the 15 electron volts.
yeah,
Also, quite high energies as well, although about 1,000 times lower than Pueo. And this is an ongoing process of trying to unfold the neutrino universe at the highest energies.
yeah.
We've observed neutrinos from supernovae. We observe them from the sun routinely now. Um, we are starting to unlock this process of using large natural media as telescopes, using all of Antarctica as a giant telescope. That's really what we're
Yes,
doing. Let's hope that the ice hangs around long enough for us to
yes.
do our best with it. And I think it is something that we all have to be good stewards of the earth that we have. It is just such a remarkable ball that we live on, and all of the secrets that we learn from physics and from other sciences
Mm.
in Antarctica are irreplaceable. So
Yes, I haven't really thought about this, Peter. So yeah, so all the environmental issues that we are having, we could potentially end up with destroying things that we need to actually see things in some ways. It's not
yeah,
like
I'm
we're all going to choke to death because of lack of oxygen, but there are higher implications of what we are doing.
yeah, it is certainly true. I you know we there are our arrival in the 19th and 20th centuries has led to some really remarkable advances in science and knowledge, but also the Industrial Revolution has cost us, and it's caused the loss of many species. Let's hope that we don't lose scientists as a species as well.
So let me ask you one last question. So um, as you and Abigail goes to further and further sensitivity, Do you expect to see things that will challenge the standard model in any way, or we are sort of confirming
Oh,
what we
we
thought?
always hope to flip the standard model on its head. Anytime there's any chance of that, I'm ready. I'll sign up for that. I'm down for it. So,
Yeah.
I think all physicists enjoy riling things up a little bit and turning the tables on the existing theories. As an experimentalist, what I really care about is what is true about the universe as an experimental physicist and any experimental scientist. What is true about the universe? What is not true about it? How can we find out and learn that to even greater levels of sensitivity? And what wisdom can we gain from it?
Yeah. Yeah, as somebody who knows nothing about physics, I always like new physics because I can start in the basement
Mm, yeah.
and get my way up there. So I think an exciting time. I have Wendy Freeman coming on a couple of days. She has been on the show before. We have this Hubble
Yep.
tension thing going
Sure.
on. So a lot of interesting things going
Yes,
on in
absolutely.
physics. Yeah,
Sure.
it's an exciting area. Yeah, thanks, Peter. Thanks so much for spending time
Thank
with
you,
me.
Gil. My
Thank you.
pleasure. All right.